All right, good morning. I'm John Goes, and I love functional programming. And I love static types. And I love the Scala programming language. And when we use all three of these things together, we have an unprecedented ability to ship code that is more correct and more principled than ever before. But that doesn't mean all is sunshine and rainbows, because even when we do FP using static types in the Scala programming language, when we deploy code into production, sometimes things go wrong. They go very wrong. And in modern async and concurrent applications, it's not always easy to figure out what's causing the problem and fix it. So today, in this talk, what I want to talk to you about is how you can use a library called ZIO to make it easier than ever before to troubleshoot production issues in your modern async and concurrent applications. And joining me will be my good friend Salar, and co-contributor on some of the features that we've recently added to ZIO to make troubleshooting async and concurrent applications easier than ever before.
Hi everyone, I'm excited to be here at Scale by the Bay alongside John. Like I said, I am loud. I don't really need a mic. This is my first conference talk, so please bear with me, and apologies if I make any bloopers. Thank you.
First conference talk. Let's give a round of applause to Salar for stepping up here on stage. That's the right way to welcome a first-time speaker. Thank you for doing that. So today we're going to start off by acknowledging the fact that when we troubleshoot issues, production issues in our async and concurrent applications built using Scala's Future, it's not always easy. In fact, it's the opposite of easy sometimes. And then we will take a sort of whirlwind tour to ZIO, which is a next-generation library that helps you build async and concurrent applications. And then we'll look at some of the goodies built into ZIO to make it easier to troubleshoot production issues in your modern applications. And then finally, we'll wind up with a little summary and sort of further resources. So if you got interested in some of the stuff we talked about today, you'll know where to look to find more information. So Moore's Law died roughly 2005. That's when processors stopped getting faster. But they didn't stop making CPUs with more and more transistors. That kept on going. We just started to get more and more cores. So modern servers, they have dozens of cores in some cases, and that made life really hard for us application developers, because suddenly we're thrust into a world where we have to do concurrent and parallel programming. And all apps have to do that. If they want to be efficient, if they want to minimize latency and maximize throughput, they have to be concurrent. But it's not enough to just throw threads at any problem, because threads actually are not that efficient. And if you create thousands of threads and you have most of them just waiting on other threads to compute results, then you're actually going to slow your application down. And so to solve this problem, we've switched over to this model of non-blocking computation known as asynchronous programming that efficient applications have to embrace. 100% of all modern applications, they have to be concurrent and they have to be asynchronous in order to maximize throughput, maximize efficiency, and minimize latency.
Now, John, I totally have a buy-in into the fact that we need to use async and concurrency for all of our apps. But whenever I have used async and concurrency in production, I have hit a number of problems that I've always had to troubleshoot when I make use of the future code in Scala.
All right, fair point. Tell me more.
For example, when things go wrong, I get a stack trace like this with not a lot of useful information for me to help me.
Yeah, that's right. So if you've ever used Future and you've done a stack trace on one of the exceptions in there, you actually don't see the chain of operations that led to the failure. You see a bunch of stuff relating to the guts of Future. And you see the guts of the fork join thread pool in there, and lots of other stuff that's not relevant, that doesn't help you solve the problem. And that's because Future, because it's built for async programming, keeps on submitting work to the thread pool, which starts off with a fresh stack trace. So all that information on the provenance of your failure is erased.
Now this is made worse by the fact that whenever I want to see what all my features are doing, again, I look at the thread dumps to find that information, and again, the information is not useful to me.
Another good point, because in synchronous applications, right, when we want to figure out what's going on, if we have like some part of our application that's stalled, we just do a thread dump and we can see all the threads in the system and we can see their state and we can see which ones are waiting on other threads. There's actually no way to do anything like a future dump when you're using Scala's future. Because when you do a thread dump with a future-based application, you only see the futures that are actively running now. You don't see the tens of thousands or hundreds of thousands of other futures that aren't running right now because they're waiting for someone to complete some promise somewhere.
And the other kind of errors that I always struggle with are when the futures are hanging or something is blocking it. Again, I struggle to find information about it.
Right, so in the world of synchronous programming, if we have one thread that's waiting for another thread to release some sort of monitor, then we can see that in the thread dump. We can know why our application is hanging because we can see that in the thread dump. However, when we've got one future that's waiting on another future to do something, we don't see that anywhere because there is no such thing as a future dump. And not only that, but with futures, both of those futures can actually be garbage collected, which means all evidence of the hang can just magically disappear from the heap. So these are all legit problems. I'll give you that, Salar. These are all legit problems with Scala's future when it comes time to building async and concurrent applications. However, future is kind of old at this point. It's 10 years old. And we, as developers in the Scala community, have had a lot of time and production experience to learn from the mistakes of future and build something better. So now I'm going to talk to you a bit about a library called ZIO that Salar and I are co-contributors to that helps you build modern async and concurrent applications in a way that's better than future. So ZIO is built on a next-generation fiber-based concurrency model.
Now, John, what is a fiber and how does it compare to a thread?
Good question. So threads, JVM level threads, are mapped one-to-one onto operating system level threads. And threads are big, heavyweight things that consumed a fixed amount of resources. They have a pre-allocated stack size and so forth. They're relatively slow and they consume a lot of resources. And as a result, a modern application can't actually scale past about 10,000 threads before the overhead of all the threads just starts eating into the performance of the application at unacceptable levels. So ZIO's fibers, on the other hand, are kind of like lightweight green threads of execution. They're super cheap. And unlike normal threads, ZIO fibers don't block. They're 100% asynchronous, which means instead of blocking a thread to wait for some other fiber to compute something, they just go to sleep. And when they're going to sleep, they don't actually consume any thread resources. Which means that unlike threads, we can scale well past that 10,000 K limit. We can get into hundreds of thousands or even millions of fibers without running into performance problems.
Now, my top three pain points with Scala futures are the fact that I can't cancel them. I always need to have an implicit for the execution context. And as I mentioned, the stack traces and thread dumps provide useless information to me.
Right, so all these are real drawbacks with future. And ZIO, because it was built well more than 8 years after Scala's future, had a chance to learn from some of the mistakes made with future and improve on it, to build on the shoulders of future to result in a data type that has much more power in every way than future. For example, there is no passing of implicit execution contexts with ZIO. All of that stuff is sort of passed for you in the background. It doesn't limit your ability to decide where things run. You just no longer need to pass all these implicits around. Also, ZIO gives you an ability to do precise parallelism. Future doesn't have that ability. Every time you call future.apply, that results in a submission to the thread pool. So it's very easy to get into a situation where you have 10,000 threads spawned by mapping over a list and stuffing everything in a future, doing something asynchronously. ZIO always gives you precise control of the amount of parallelism with every single operation. Like you mentioned, Salar, futures can't be canceled. And that's a big problem. Because what happens is when you stop waiting for a future to be completed, or when a bunch of futures that you're sequencing or traversing, one of them fails, all the other futures keep on running in the background, consuming resources. They consume network resources and memory resources and so forth. It's not uncommon in a modern application to have tons of threads sitting around executing future logic for results that are ultimately going to be thrown away. And ZIO, on the other hand, supports cancellation. So when a resource is not needed, it gets canceled right away, and all resources are safely cleaned up. Stack traces, like you mentioned, are totally useless with Future. ZIO introduces something called an execution trace, which is better than a stack trace, gives you more information than a stack trace, and it works across asynchronous regions in your code, as well as parallel regions. It's not really possible to refactor Future-based code, because if you extract out some variables in some Future-based code, then you might get a different ordering of the results in which those futures are run, because Future is an eager data type. And not only that, but in some cases it will change the number of times those things happen in the real world. ZIO, because it's based on a lazy data type, you can refactor your code all day long without changing its behavior. Future, because it's eager, you actually can't write Future-based combinators. For example, you couldn't write a retry function that takes a future and returns another future that will do the effect of the first one a certain number of times until it succeeds. You can't write that with Future. But because ZIO's effects are lazy, it's very easy to write that type of logic. Future has an error channel baked in, but it's always fixed to be throwable. And what that means is when you have a future, you never know whether or not an error has been handled. And so sometimes you're going to assume that an error has been handled in a future, but you're going to be wrong. Some error sneaked into that future, and it's going to blow up your application in an unexpected way. That's because Future's errors are dynamically typed. ZIO's effects, on the other hand, have statically typed errors. So you can describe whether or not effects fail, and if they do fail, how they fail. And you can use the Scala compiler to enforce that. Future has no version of try finally that works across async operations. ZIO gives you a version of try finally that can work across async and parallel regions of your codebase, so that you can make sure if you acquire some resource, you definitely end up releasing it. So you can build applications that don't leak resources. Future is a reasonable way to do async and concurrent programming. However, it doesn't provide you any tools that you need in order to build concurrent applications. So for example, you don't have any async version of Java's blocking queue, or of a semaphore, or of a lock, or all the wonderful stuff in Java util concurrent. Future doesn't give you async versions of any of that stuff. And ZIO, on the other hand, gives you an async version, a high-performance async version of all the goodies you've come to know and love in the Java util concurrent world. Future is known for not so great performance, and that's because by default it submits every operation to a thread pool, which interferes with the way that modern CPUs get a lot of their performance, which is by caching stuff in core local caches. And so when you submit every operation to a thread pool, you end up basically starting from a bunch of cold caches and having to warm those caches up. ZIO will batch, by default, more than 2,000 operations on a single core before a fiber yields to other fibers. And then finally, Future-based applications are not easy to test, but ZIO, because it's based on pure functional programming, adds a feature called late binding that makes it very, very easy to test your ZIO-based code in a deterministic fashion that runs quickly without actually interacting with the real world. In this example, you can see a hello world application with ZIO. It extends ZIO.app, and our main function here, called run, gets to return an effect that it creates by calling putStirLine with a string hello world.
Now, John, out of curiosity, what does the .fold do? Why do we need it?
Good question. So putStirLine returns an effect that succeeds with a unit value. But the run function requires we return an effect that succeeds with an integer status code, which will be used as the exit code for the process when our main application terminates. So what we do is we fold over both error and success case, mapping the error case to the integer 1 and the success case to the integer 0 to end up getting an effect out of that, which succeeds with an integer value. In this little example, we can see an interactive application that prompts the user for their name, reads it, and then writes it out back to the user. And you can see sequential flow here. However, notice we are not programming with statements. So you don't program with statements using ZIO. You program with values and operations on values. In this case, we have 3 different effects, and we're composing them together with FlatMap. How we do that in a more sane fashion is we use for comprehensions in Scala. And every for comprehension in Scala, your intuition for that should be, hey, this is somewhat like a statement. But instead of doing side-effecting eager operations, we're just building a lazy effect out of this for comprehension.
Now, looking at the code, John, I see that my app is extending app. Do we get any extra batteries included with the app?
Yeah, so because ZIO effects are totally lazy, that means if you want to see what they do, you have to run them. And to run a ZIO effect, you need a runtime system, which bakes in the sort of core logic of the ZIO interpreter. And it uses a thread pool, and it has an error reporter that's called with any of the errors in your application that aren't handled, so you can log those and make sure you don't lose them. And app, ZIO.app, actually bakes in that runtime system and uses it to execute the effect that you return from run. In this example, you can see how easy it is to define new combinators on ZIO effects. In this case, I write a combinator that allows you to take two tasks and return a new task that computes both of the other things in parallel. You can see how easy it is to do this with a fiber-based concurrency system. You simply fork the left task to get a left fiber, and then you fork the right task to get a right fiber, and then you asynchronously join the left to get the A out of the left-hand side, and you asynchronously join the right to get the B out of the right-hand side, and then at the bottom of that for comprehension, you yield a tuple that contains the A and the B. This is how easy it is to do parallelism with fork join.
Now, John, what will happen if one of the fibers fail?
Good question. So if something fails in the middle of that for comprehension, if one of the fibers fails and hence the join fails, then what's going to happen is the other fiber will be gracefully shut down instantaneously, and all resources will be safely cleaned up. And that happens because we're calling .interrupt children on the effect returned from the for comprehension. In this bit of code, we have this HTTP GET method that for a given URL gives us back a task of a response. And maybe we have this particular URL that's kind of flaky and we need to retry it a bunch. So what we could do is we could call this retry method on effect, and we can pass it a schedule, a retry policy that tells us how we want to retry that. And we're going to get back a new task, a new effect, that's going to execute the other one according to the specified retry policy. In this case, our retry policy does exponential fall off, starting from 10 milliseconds and then going to 20, then 40, then 80, and so forth. Or once that reaches more than 60 seconds, it's going to fix spacing between the retries to 60 seconds, and it's going to do all of that up to a maximum of 100 times. And finally, in this last example, we're going to use the same HTTP GET method to create a load tester. And this load tester we're going to create quite easily. We're actually going to do a for each loop over the integers from 1 to 1,000. Only instead of calling ZIO for each, we're going to call the parallel version of that, ZIO.forEachPar, which executes every iteration of the loop in parallel. So in parallel, we're going to be executing all of these things together, doing HTTP gets for the same URL, thus creating a load tester that's executing 1,000 concurrent requests. And then if we wanted to do that repeatedly, we would just add .forever onto the end of that effect, and that would put it in an infinite loop that keeps on pounding our server with 1,000 requests per second, or per whatever. So that's unfortunately all the time we have to show you about ZIO. ZIO is a very rich library, and I encourage you to check out other talks on the topic. For now, though, we're going to move on to take a look at that sort of tool bag that ZIO gives you to troubleshoot production issues in async and concurrent applications.
Now, John, before we carry on, does ZIO provide anything for us to prevent problems in the first place going to production?
So good question. So ZIO gives us a few goodies that can help us prevent us from shipping issues that lead to production errors. And one of them is testability. So in this screenshot here, you can see an application that reads and writes from the console and sleeps and so forth. And it looks like this would be hard to test, but because we're using ZIO, which is based on pure functional programming, and because ZIO has very, very good support for late binding, it allows us to test this deterministically using ZIO test. So in this test, we're actually verifying that it's interacting with the console in an appropriate way, and we're advancing time inside our test, this test will run deterministically and instantaneously without any interaction with the outside world. And you can do that for any ZIO application you write. You can write tests that run deterministically and instantaneously without interaction of any kind with the outside world. Also, Future has this dynamically typed error channel, which means that when you have a future, you never know at compile time if that future is going to fail. But what ZIO does is it takes that error channel out and sticks it in a type parameter in the ZIO effect type. It's the second type parameter. And so that gives you the possibility to plug in your own error type. So if you want to use your own ADT, your own data type for custom errors, business errors, domain errors, you can do that. You can also plug throwable in there if you want, why not? And then you have basically what you get with Future. But if you want to describe effects that cannot fail, you do that by plugging nothing into that type. And because in Scala there are no values of type nothing, this represents a compile time guarantee that this class of effects with nothing as their error type cannot fail. And when you have the ability to statically represent effects that cannot fail, it helps you reason about, with the help of the Scala compiler, the error behavior of your application. In this case, we're using the Scala compiler to help us prove that this process defect cannot fail. We call process upload, and that can fail with some sort of upload error, but then we call the or else operator on that effect to have a fallback, and our fallback cannot fail, and we know it by looking at its type, and the Scala compiler knows it, so we're able to prove at compile time that we've handled all errors in this chunk of code.
Now, John, I've heard that with try and finally, some errors get lost. Is that true?
Yeah, and not just with try finally, but even with Future. These are lossy error models. And let me give you an example of where that happens. Let's say we're doing one thing, and then we fork that off into two different threads. Now we have one on the top and one on the bottom. And then let's say the thing on the top fails with an error E1. And then let's say the thing on the bottom fails with an error E2. And as it's failing, it has a finalizer installed. And let's say that finalizer is poorly behaved, and that finalizer fails as well. And what's going to happen in this case? Well, E1 is the one that will get reported back. It's the one we'll be allowed to catch in Java and Scala, and it's the one you can recover from in the future. E2, on the other hand, gets thrown away entirely. You're not going to see that in any log file. It's not even visible to your application. And then the finalizer error gets reported, at least with Future, it gets reported on a side channel. So ZIO says, no, this is not a great state of affairs. It introduces this new data type called cause, which comes from functional programming. It's a free semi-ring. And what it does is it allows lossless capture of 100% of all errors in the events of a failing effect, whether they're async or concurrent errors. And so it captures the E1, it captures the E2, it captures the finalizer error as well inside this data structure. And when you go to pretty print this, you can actually see which errors occurred in parallel with which other errors, and which occurred sequentially, which errors are primary errors, and which errors are secondary errors. You have 100% of all that diagnostic information to figure out what went wrong.
Now, John, tell me, how does this execution traces actually work?
Yeah, so execution traces, unlike stack traces with Future, tell us every single line of code leading up to the failure. Not just every single method, but every single line of code, even in a for comprehension, leading up to the line that failed. And not only do they tell us what did happen in the past, they also tell us what would have happened in the future had that line of code not failed. And you can see here the amount of information we get out of these execution traces is tremendous, and it allows us to figure out all the steps that led up to a given failure so we can troubleshoot and fix production issues faster, way faster than we could with Future, without any print lines.
Earlier I asked if with Scala features I can't see what all my features are doing. With ZIO, can I see what all my fibers are doing?
Absolutely. So ZIO is the only library out there that allows you to do a fiber dump, which is the analog of a thread dump, but for fiber-based concurrency systems. And this fiber dump, which is modeled after a thread dump, so if you've ever used JStack or something like that to print out everything that's going on in your Scala application, then you're going to be familiar with this format. We can see that fiber number 17, which has been executing for 41 milliseconds, is currently waiting on fiber number 14 to do something. Not only that, but we can see that it's suspended. It's currently interruptible, so it could be canceled from the outside. It has done 0 async operations so far, and we can see the exact line of code where it's waiting on fiber number 14 to complete. And then in addition to that, of course, we get the full execution trace, which contains the history of all operations leading up to the point where it was suspended.
Now, John, does it solve my problem of having visibility over hanging fibers?
Yeah, absolutely. So remember, when one future is hanging on another future, there's no way to see that. And so people insert lots of print lines to figure out why parts of their future-based application just stopped. And it's a huge problem. Even the print lines won't help you if those futures are garbage collected, which they probably will be in a lot of cases. So what ZIO does is it actually tells you when you've got one fiber waiting on another fiber to be completed. In this case, what we do is we make a promise, we hand that promise off to some other method, and then we have another fiber that's sitting around waiting on the result of that promise, and we can see inside the fiber dump, we can see that that fiber, which we forked off in that line in the for comprehension, is currently suspended on the fiber that created the promise, allowing us to, for the first time ever, to diagnose quickly issues where our application, part of our application just hangs because no one completed something. And then another ZIO first is actually necessary because ZIO effects can be canceled. You can cancel them. You can't cancel futures, so futures don't have this problem. But what happens in a ZIO application is a future or a ZIO effect just stops executing because someone canceled it. And sometimes that leads to a problem. You're left wondering, well, who canceled it and why? Maybe it wasn't supposed to be canceled, and you've got to figure that out. So whenever an effect in ZIO is canceled, ZIO will actually tell you which fiber it was that canceled that effect. So you can figure out why part of your application just was interrupted. So as we've seen in this presentation, when you go to troubleshoot an async concurrent application built on Future, it's not easy. You run into all sorts of problems. You run into problems because you can't do anything like a future dump. You can't dump out all the futures running and see what their state is. You can't do that. You don't get any kind of useful stack trace out of future errors. And then you have this issue where when futures hang on other futures, there's no insight into that, and all evidence of that hang can be garbage collected. So you really are crippled when it comes time to troubleshoot issues with production applications built on Scala's Future. ZIO, however, is a next generation take on Future. It's designed as a modern fabric on which to build async and concurrent applications. And it takes the opportunity, complete brand new design, to learn from our 10 years of production experience with Future to build something that's better. And then it comes with, especially as a result of some recent contributions that Salar and I have been working on, it comes with a set of tools that no other fiber-based concurrency system out there has. And these set of tools allow you to do fiber dumps so you can see all the state of all fibers running in your application. They allow you to do execution traces, which are on by default. There's nothing you have to do to get that. It's just out-of-the-box support for that. And they also allow you to see when one effect is waiting on another, you can see that information. You also have lossless errors that never throw away any information. So you're never left wondering what happened because you got some sort of secondary failure in the log file, but the actual true cause of the problem was thrown away either by Java's try finally or Scala's try finally or by Future's error handling scheme. You get lossless error model. And you also get statically typed errors, which means that you can use the Scala compiler to help you get the error behavior of your application right before you ever deploy to production. So if all this sounds interesting, I encourage you to check out some of the other talks that I've done and other people have done about ZIO, or check out the website. There's lots of great resources for learning more about how a library like ZIO can help you build modern applications that are async and concurrent, but in a way without all the drawbacks of Future. I want to give a special thanks to Alexei. unfortunately, I don't see him here. He must be off organizing this conference. I know he worked very hard to bring us this conference, so I want to thank him for inviting me and Salar to do this presentation. And also, I'd like to announce that early next year, we're going to be doing a ZIO hackathon here in the Bay Area. This is a great chance to come and hack on ZIO, the ZIO ecosystem, the broader ZIO ecosystem, but also we have an unconf there, so it's a great opportunity to learn a lot about ZIO and the bigger ecosystem. We've done 2 of them so far. We've done one in Warsaw, which was about 60 people, and one in Berlin, which is about 120 people. And who knows how big the one in the Bay Area will be, but I expect lots of good things from that. So please look out for that, and I'm sure Salar will announce it to the local meetup. You can learn more at zio.dev, which has decent documentation, but it's always in need of improvement. Pull requests, welcome. And then we have a great Discord community. Discord is brand new. We've just been using it a few weeks, but there's already more than 500 people on there, and they're super helpful and eager to help out anyone who has any issues. Also, Stack Overflow has a growing ZIO community to help out with any issues you might run into. You can follow me on Twitter at JDGoes. You can support my work, especially my work blogging and speaking at conferences on Patreon if you want. You get a few free goodies on the side. And then you can read my blog at dgoes.net, where I quite often blog about functional programming in Scala.
And feel free to follow me on Twitter and my blog as well. I won't try to spell my name for you, it's long. Where I'm hoping to have a lot of content on what's happening in ZIO, and of course the Scala community here in the Bay Area as I run the meetup. Thank you.
All right, thank you so much. I'll take questions in the hallway track since we're out of time.